Good morning, students. Let us have a brief recap of why we are considering the crystal oscillator. We had seen the RC phase shift oscillator, which works in the audio frequency range. Later on, we had seen the Hartley and Colpitts oscillators, which work in the radio frequency range. There are many other types of oscillators also, but they are all similar to this Hartley and Colpitts only in the radio frequency range. There are many other types called clap oscillator and many such things. But let us not discuss all that. It is out of our curriculum as well. We had kept them out of curriculum because they are all similar in their functioning. But this crystal oscillator is slightly different from the previous types of oscillators. But the Barkhausen criterion is going to be met here as well, even in the crystal oscillator. That is common to all the oscillators. So I was telling you about the basic functioning of the crystal yesterday, how the piezoelectric effect is going to help us, as each crystal is going to have its own natural frequency. Now in the earlier oscillators, we were dependent on the values of the passive components for the desired frequency of oscillations. But in the case of a crystal needs to be polished and it has to be manufactured in a particular size so as to get a desired frequency. That means, yesterday I was telling about the 32 kilohertz crystal, which is used in our all watches and clocks. So the 32 kilohertz is a very accurate frequency, and that frequency is given to a divider, and it is divided by 32, and the output is 1 hertz. That 1 hertz is going to be given to the seconds needle in the wristwatch or in the wall clock, if it is a analog type of watch. If it is a digital type of watch with an LCD display, then the same 1 hertz is given to the LCD display as a pulse, and it will keep blinking in your wristwatch or in the digital clock. So now this crystal has its own natural frequency and it is very much accurate. Accurate in the sense, most of the time the crystal's natural frequency is independent of the atmospheric conditions as well. You already know that the resistors have this positive or negative temperature coefficient of resistance, and capacitors have their own larger tolerance. But the crystals, as they have natural frequency based on their dimensions, they can be used in all those applications where timing has to be really very accurate. So in general, the crystals will work right from 32 kilohertz till 10 megahertz. And basically, the frequency of oscillation depends on the size of the crystal, in the sense, if the size is more, frequency is less. If the size is less, frequency is more. Means if you want to have a crystal which has to work at 32 kilohertz, you will have a slightly bigger sized crystal. And if at all you want to have a crystal which has to work with 10 megahertz, you will have to have a smaller size, because the frequency of vibration is inversely proportional to the size of the object. So that way we are going to use the crystal oscillator for obtaining accurate frequencies. Now you are seeing the equivalent circuit of a quartz crystal here. Even though crystal is made of a quartz stone, internally we can represent it by means of the equivalent circuit that is shown at the right side. For that matter, electrical science can model anything and everything in this universe in terms of inductance, capacitance and resistance. Whereas mechanical science can represent anything and everything in this universe in terms of voltage, temperature and, not voltage, volume, temperature and pressure. The civil engineering people can model anything and everything on this universe, in this universe, using stress and strain and load. So that way, each engineering branch has got its own basic elements by means of which modeling happens. Now, in the electrical sciences, we have these passive components, and using the passive components, anything and everything can be modeled. In fact, even the human body can also be modeled in terms of resistance, capacitance, and inductance. Already such body model is available. It is called HBM, human body model, that is available. Why they have made such a model is that whenever human beings touch the integrated circuits, based on the property of the human body, there can be some functionality problem or functionality disorder even with the integrated circuits. The human body's charge can be discharged to an integrated circuit, causing the malfunctioning of the integrated circuit itself. That is why they have modeled human body as well. So that way this crystal is modeled by means of these four passive components. You can see this R represents the internal friction, which means when a voltage is applied to this crystal, let us say a voltage is applied to this crystal. Now the voltage cannot pass through the crystal. That means current cannot flow through the crystal. That means there is a friction that is represented by R. So let me annotate with a different color. So this R represents the internal friction, and L represents the vibrating mass. Now when the crystal starts vibrating within, actually it is the energy that is going to try to flow through this component, but as there is an insulator in between, energy is unable to flow. But the insulator or the quartz crystal itself starts vibrating. Now when it is vibrating, it has got a mass, it has got an inertia, and there is this storage to some extent of energy, and the storage of energy is in the form of electromagnetic only. Now you may think, why crystal will have electromagnetism? Crystal is not having electromagnetism. Magnetism is omnipresent everywhere. The gravitational field itself is present everywhere, and due to which there can be inertia. And that vibrating mass can be represented as inductance. Now, the series capacitance is represented by a crystal compliance. Now, this crystal will have a series capacitance as well as a parallel capacitance. Okay. As it is an insulator separated by two metal plates, crystal is basically a capacitor. So its series capacitance itself is represented by this C. What is compliance? Compliance is 1 over capacitance. It is also called as elastance. So here crystal compliance is mentioned here. Basically it is a capacitance. Only thing is it is reciprocal. Compliance and elastance both are one and the same. Different people use different terminologies here. Now this Cm, which is in parallel, this capacitance is due to the mechanical mounting of the crystal. Now you can see there is one RLC series circuit, there is one Cm parallel circuit. Now this Cm is basically the complete capacitance of the crystal, that is because of the mechanical mounting, which means what? An insulator is separated by two parallel plates of conductor. So that is what is the Cm. Now why is this C in series? That is because of the crystal's own compliance, the material's own compliance itself. That is why it is given in series with RLC. Now you can see there is a series resonance, there is a parallel resonance in this circuit, which means RLC together is going to be a series resonant circuit. This whole thing is going to be a series resonant circuit. But you will have this Cm also into picture. Cm is in parallel with this RLC. So you will have RLC parallel with Cm, due to which you will have parallel resonance. Which means the crystal can have two frequencies now. The same crystal can have two frequencies. One is a series resonant frequency, one is a parallel resonant frequency. We can use any one of them depending upon how we use the crystal. If we connect the crystal in series with the feedback circuit in that way, now we can predominantly choose the series resonant frequency only. If at all you connect the crystal in parallel at the output of the amplifier, of course, again by making a feedback connection appropriately, we can make use of the parallel resonant frequency of the crystal. We will see that in our examples in the next slides. So as we can represent the crystal in the form of an equivalent circuit, let me show you the oscillator circuit itself, which we are going to use now. So, characteristics of the quartz crystal, it exhibits two resonant frequencies. One is series resonance. When the impedance is low, then there is series resonance. But when the impedance is high, when the reactance of the series resonance equals the reactance of the CM or the mechanical mounting capacitance, then we have two. If the impedance is very low, let us say this R is very low. When the R is very low, we will have L and C, then it is series resonance. But when the reactance of the series resonance equals the reactance of the CM, then it is a parallel resonance. So you can see this F1 corresponds to series resonance and F2 corresponds to parallel resonance. In the case of the series resonance, there is minimum reactance. In the case of parallel resonance, there is this maximum reactance at two frequencies. Parallel resonance is also called as anti-resonance because there the reactance or impedance is increasing. You can see the y-axis is Z here, x-axis is frequency here. But F1 and F2 will not be actually far away. When we use the crystal, even though there are two frequencies, they are not really very far away, they are nearby. We will see that in the exercise. So how to connect the crystal oscillator now? You can see there is a regular RF choke, then there is a voltage divider bias network using BJT, and you can see the crystal connected between output back to input. And there is one coupling capacitor together with the crystal. Why this coupling capacitor is connected in series with the crystal? You have to visualize the equivalent circuit now. To the equivalent circuit, there is one more capacitance connected in series now. We want to have a series resonance predominantly. That is why we can use this coupling capacitance here, this CC, in series with the crystal, so that the parallel resonant counterpart of the crystal can be completely ignored that way. It need not be functional that way. As I showed you in the previous slide, when the impedance is low, it is the series resonance which is going to work. At that time, the parallel capacitance will be ignored. When the impedance is very high, then the parallel resonance comes into picture. So, using this logic, if we connect one capacitance in series with the crystal, automatically the series resonant part of the frequency is going to be utilized. Now you can see, in the case of this feedback network, we did not think much about beta. Why? Crystal has got its own natural frequency. But still, beta is going to play a role here. A into beta is going to work here. But that beta is dependent on the capacitance also on the crystal. So the Barkhausen criterion is going to be applicable here as well. Only thing is that in the earlier cases we had 1 over 2 pi r c into root 6 or 1 over 2 pi square root of LC in the previous oscillator circuits. Here we have no such formula at all. Whatever is the natural vibrating frequency of the crystal, that itself will be output here. See, as soon as the circuit is switched on, there will be DC across this crystal. You can see here, there is this RF choke, there is this R1. So there will be to some extent a DC. Let me annotate. As the right side is an RF choke, let us say this is plus, this is minus, which means voltage at the collector will be somewhere around VCC by 2 and voltage at the base will be lesser. So there will be a voltage across the crystal as well as this voltage is applied. Now you may think this capacitance is there due to which DC may not pass this side. Yes, but as soon as you switch on, an impulse will be passed, right? As soon as the circuit is switched on, an impulse will be passed through the capacitance until the system stabilizes. That impulse is enough for the crystal to start vibrating. Now when the crystal starts vibrating, that vibration will come to the base and through the amplifier circuit it will be amplified. That amplified signal is fed back through this capacitance back to the crystal. Now the crystal is part of the feedback path, so the same signal will keep on making the crystal also to keep vibrating. Otherwise, we could say that initially only because of the impulse there would have been a damped oscillation, or else after a few moments oscillation would have died out. But because this amplifier is connected, the signal will get amplified and it will be fed back to the crystal and it will go on like that. Now this is series resonant circuit. Now let me show you the parallel resonant circuit. This is the parallel resonant circuit, where you can see the regular RF choke and the voltage divider bias network, but now you can see the feedback is given to the emitter. So this circuit works like a common base circuit now, and this crystal is connected with respect to ground now. See, from the base, so from the output it is connected to ground now, and part of the output is fed back to the input by means of this capacitance C1. Here the CC was connected in parallel with the crystal, in series with the crystal. Here C1 can be considered as in parallel with the crystal because of the connection this way. Now the same point, whenever the impedance is very low, then the series resonance is going to work, but otherwise the parallel resonance is going to work. Here the crystal itself is connected as a parallel resonant circuit along with the amplifier. So that way we will have the anti-resonance frequency in the second circuit. Now the formula for the series resonance is 1 over 2 pi square root of L into CS, where CS is that series capacitance which was there in the equivalent circuit. Now the formula for parallel resonance is 1 over 2 pi square root of L into CP, where the CP is the parallel combination of both of them now. In the equivalent circuit we have seen that CM and CS, series capacitance, which is also called as compliance there, and there is a mounting capacitance. So as they are in series, now the parallel capacitance itself is the effect of those series things. How they are in series, when both are working together, when it is connected with respect to ground, those modeling capacitances are in series. When the capacitances are in series, you will have a equation which is generally of the parallel form of the resistors. So I will not go into all those details about how that capacitance is in series that way. That is again part of your circuit analysis. See, now when the crystal starts vibrating, we can say in this manner it is in series. Both the even though in the equivalent circuit both are in parallel, when resonance happens, both are in series. So the effective capacitance Cp is actually the parallel combination. So that way we have these two formulae. Now let us have an exercise. Let us try to solve a problem. Given L is equal to 3 Henry, CS is equal to 0.05 picofarad, R is equal to 2 kilo ohms, and Cm is equal to 10 picofarad, what is the series resonant frequency of the crystal? Can anyone calculate it quickly and tell me the answer? I will show you the formula once again. Fs is equal to 1 over 2 pi square root of L into Cs. It is like the earlier Hartley and Colpitt's formula only. Only thing is this L is internal to the crystal, Cs is also internal to crystal. It is 1 over 2 pi square root of L into Cs. L is given as 3 Henry and Cs is given as 0.05 picofarad. Can you tell the answer? I feel something wrong with my slide. It cannot be 3 Henry as such. Let me verify that later on, but you calculate and tell me the answer. Sayan has given the answer 1.030. Rohit has given the answer 129.94 kilohertz or 130 kilohertz. Let me see what is my answer. The answer is 411 kilohertz. I feel something wrong with the values here. Let me verify later on. Even I am not sure now. Okay. I am not really very sure about this value. Let me verify. I will tell you in the next class later on. Okay. Can you show the formula once again? Okay, let me show the formula. Fs is 1 over 2 pi square root of L into Cs, where you have to substitute the value of inductance and capacitance, series capacitance. Now, for Fp, we need 1 over 2 pi square root of L into Cp, where Cp is nothing but Cm into Cs divided by Cm plus Cs. The mounting capacitance and the compliance, its product divided by its sum. So, this is the formula. Even though R is given there in that exercise, R is not going to be useful to us in any way. Only thing is, if R is very low, then it is the series resonance that is going to work. If the R is very high, then it is the parallel resonance that is going to work. That is how we have to configure the circuit as well. So now, let me show you. Can you calculate the parallel resonance frequency? I am doing it, I have shown it anyhow again. Fs is 411 kilohertz. Now Cp is 0.0498 picofarad. It is Cs into Cm divided by Cs plus Cm. That is 0.0498 picofarad. You can see here it is 0.05 picofarad, here it is 10 picofarad. Whenever we have a parallel formula for two values, whichever is the least value, our effective value will come nearer to the least value. That way, 0.0498 picofarad is very much nearer to 0.05 picofarad. Now, when you substitute that in the same formula, we get parallel resonant frequency equals 412 kilohertz. Now, you can see between this Fs and Fp, only 1 kilohertz difference is there. This side it is 411 kilohertz, that side it is 412 kilohertz. That means only 1 kilohertz difference. That is why in most of the cases, when we use this crystal in let us say 10 megahertz range, then in even the 1 kilohertz difference between series and parallel will not make a difference at all, because the output is available at 10 megahertz. That 1 kilohertz will not make a difference at all. That can be ignored in such cases. Whereas if at all we use the crystal at very less frequencies, then it will really make a great difference. For example, in the case of the wristwatch, if you use a 32 kilohertz crystal, and let us say there is a parallel frequency of 33 kilohertz, series resonant frequency of 32 kilohertz, then that 1 kilohertz is actually going to make a big difference. The actual frequency may be in between both of them. It may be 31.5 kilohertz, where our timings will have issues. So that way, when we use the crystal for low frequency applications, and if the output frequency has to be accurate, then the circuit has to be chosen in that manner only, as I have shown you in the previous slide now. Series resonant circuit or parallel resonant circuit has to be configured that way. Otherwise, in many cases, we will have a combination of F1 and F2 or Fs and Fp together. In the higher frequencies, we can ignore them. Okay, let me verify these values once again on my side, and let me tell you the answer in the next class. Now with this, I have come to the end of module 4. So let me stop sharing this slide. In this module, we have discussed about feedback and oscillators. In the beginning, we discussed the negative feedback and its advantages and its methodologies. Later on, we went to discuss the positive feedback, and then we have discussed the application of positive feedback in terms of oscillators. So with this, let me stop sharing this slide and let me start sharing the next set of slides, that is module 5. Okay, now we are starting module 5. In module 5, we are dealing with the power amplifiers. This is the last part of our course. We had discussed about the usage of amplifiers right from the beginning, but we were always working out with the small signal amplification. Means always we thought that the signal is small enough that it will not affect the switching operation of the transistor. That means the signal is small enough so that the Q point is not going to be affected. So that was called as small signal amplifier. In this module, we are going to deal with large signal amplifiers. Let me tell about that later on. Let me start this module now. Let us see how amplifiers are classified in another way. Amplifiers can be classified in so many ways, based on the feedback also, based on the region of operation also. So we had seen 4 classes of amplifiers, 4 classifications of amplifiers in the previous module, like voltage amplifier, current amplifier, transconductance amplifier, transresistance amplifier. That was the different domain of classification. Now in this module, we are going to classify amplifiers in another domain based on the region of operation. Initially, we can classify the amplifier as audio and radio amplifiers, because the audio amplifiers work with the frequency range of 20 Hz to 20 kilohertz, where all our sound, voice, music needs to be amplified. Now, whenever you go to a musical concert, or whenever in our college we have cultural festivals, you can see that large speaker boxes are kept at the stage or in front of the audience. Very large loudspeaker boxes are kept. Now, if that large loudspeaker box is of the wattage of, let us say, 1000 watts or 2000 watts, 1 kilowatt or 2 kilowatt, or maybe sometimes it is 10 kilowatt, you can think about the amplifier that is utilized for driving such a large loudspeaker with the high power or high wattage output. Now, carefully such audio amplifiers are to be designed in such a way that whenever a singer is singing, by keeping the mic set near the mouth, in whatever way the singer is singing, the same sound output or the voice output should be present at the loudspeaker. That means the signal should not have distortion in case of amplitude or in case of frequency. There should neither be amplitude distortion nor frequency distortion. There should not be a clipping of the signal as well. Clipping itself is actually amplitude distortion also. So that way, the design of an audio amplifier is also not an easy task when it comes to high power. Next, when it comes to radio amplifiers, now you're all using mobile phones. The mobile phone's operating frequency is 2.4 gigahertz in the 3G band. Now, when it is 2.4 gigahertz, it is 2400 megahertz. We were discussing about Hartley oscillator, we were discussing about crystal oscillator. But we are talking about an amplifier which is going to work at 2400 megahertz. Now, how to make this amplifier to work at 2400 megahertz, where the mobile phone will have a basic operating frequency of 2.4 gigahertz. There we make use of a special purpose oscillator or special type of oscillator called as VCO. It is also called as voltage controlled oscillator. Of course, that is beyond our curriculum as such. You are going to learn about VCO in your future courses. Now, when we use a VCO at 2.4 gigahertz for producing the carrier frequency for the working of the mobile phone, now through this frequency, your speech also should be transmitted, or your SMS also has to be transmitted, or any other communication which you do through your mobile phone has to be transmitted. It may be an image transmission, it may be a data transmission, it may be a text transmission, it may be a voice transmission. It has to go through this radio frequency only, 2.4 gigahertz only. So in such a case, how to design an amplifier which is going to work at 2.4 gigahertz? That is also a big challenge. we have to design an amplifier which is going to work for 2400 megahertz frequency range. That means the transistor should not have parasitics there. In the third module, we had seen how the transistor's internal capacitance is going to affect the bandwidth. Now think about radio amplifier, where the amplifier is to work in the gigahertz range, and we should have that bandwidth also. That is the challenge. So that way, designing an audio amplifier and designing a radio amplifier, both are not easy task as it seems to be. In this theoretical discussion, it seems as if it is all really very easy. But designing a high power amplifier in the audio range is a challenge. At the same time, designing a normal radio amplifier is also going to be a challenge. And designing a high power radio amplifier is a much bigger challenge. For example, we have satellite communication now. We are going to send the frequency to a satellite, and the satellite is going to transmit it back to the earth so that we will have a satellite coverage. And all the dish antenna are going to pick up this particular signal, and you have all these television channels. Now, the point is, if the satellite is going to work at let us say 60 gigahertz frequency, 70 gigahertz frequency, 80 gigahertz frequency, right from 20 gigahertz onwards. Now, that particular transponder, which is going to be utilized for transmitting as well as receiving, it is called transceiver also. So, that will contain a radio amplifier of high power. Now, think about the signal reaching all the way to 36,000 kilometers to a satellite, and the satellite is sending this signal back to the earth for broadcasting purposes. Now that is a radio amplifier, which is a power amplifier, high power amplifier. So that way, designing of all these amplifiers is not as simple as it seems to be. So this is one way of classifying amplifiers as audio and radio amplifiers. The next one is wideband and narrowband amplifiers. Now, in the case of an audio amplifier, it is a wideband amplifier. In the sense 20 hertz to 20 kilohertz, all the sound that is being produced will be output at the speaker. But what about in the case of a mobile phone? If the mobile phone is working with the 2.4 gigahertz or 2400 megahertz, it has to be narrowband. In the sense, as much as possible, the bandwidth has to be narrow, because we are going to use a tuned application. To tell you more about a tuned application, in the mobile phone's usage itself, when multiple people use the same band, what is going to happen? Now, that is a complicated one. Let me not tell you now. You will understand this only when you come to third year and final year in detail, when you study digital communication and wireless communication and mobile communication. Let me not bring the example of mobile phone here now. That is not so easy to discuss right now. But let us think about this FM radio channel. In the FM radio channel, each FM station is allocated with the particular carrier frequency. Now, when you tune your FM radio receiver for a particular station, in between these two stations, it has to be a narrow width, because from 88 megahertz till 108 megahertz, there are totally 20 megahertz bandwidth. In this 20 megahertz bandwidth, there are so many stations, each is having a 200 kilohertz bandwidth, which means that is a narrowband amplifier. Each radio station's amplifier is supposed to work only within 200 kilohertz bandwidth. For example, if a station is having a 92.1 megahertz, then it will work only between 92 to 92.2 megahertz. That is only 200 kilohertz in between, and the center frequency is 92.1 megahertz. In such a case, it is a narrowband amplifier. So it depends on the application about whether the amplifier has to be wideband or narrowband. Now the third one is small signal amplifier and large signal amplifier. As I have told you, small signal amplifier means signal will be really very small. Input signal will not affect the Q point of the transistor. That is the idea. Now, in case of a large signal amplifier, signal will not be in microvolt or in millivolt. Now, the signal will be in volts. When the signal is in volts, it is going to affect the switching of the transistor. Now, in such case, it is called as large signal amplifier. But in the case of a large signal amplifier, there can be distortion. Now, distortion can be tolerated at times. Can anyone tell me what are those applications where distortion also can be tolerated? Whether it is amplitude distortion or frequency distortion, it can be tolerated. Can anyone tell me some applications? Okay, let me tell the application. In the case of an ambulance, a siren, distortion can be tolerated. There the quality is not important, the power is important. If there is a patient who is critical and the ambulance is traveling, if there is a traffic there and the ambulance's sound or siren must be large enough such that all the people traveling on the road will listen to it and they will give way to the ambulance. That way, even if the distortion is there in the output waveform, it can be tolerated. There, the quality of the sound is not important. The power of the sound is important. Whereas in case of a small signal amplifier, the quality of the waveform is important. In the case of our regular music or speech, the signal's amplitude is important. Whereas in such applications as an ambulance, a siren, or a very high sound which is required to alert people, in such cases, the amplitude distortion also can be tolerated. Such amplifiers are called large signal amplifiers. We are going to discuss large signal amplifiers only in this module now. So, small signal amplifier is a pre-amplifier. It works in milliwatts. Large signal amplifier is a power amplifier which works in watts. Till now, we have been discussing only the small signal amplifiers. In general, whenever we have a complete amplifiers box, there can be multi-stage amplifiers. In the beginning, there will be pre-amplifier. At the output, there will be power amplifier. To give you an example, in the musical concert or in any such function, when the singer is singing, when it is going to the amplifier box, mic set will be connected to the pre-amplifier, where it will increase the signal amplitude maybe to 20 dB or to 40 dB with the gain, let us say with the voltage gain. Now that is pre-amplifier. But when it comes to the loudspeaker is a very large apparatus and it is a high power transducer. There, after the pre-amplifier, there will be some other stages in between, and afterwards, at the end, there will be this power amplifier, which is going to drive the loudspeaker as such. So, large signal amplifier is basically a power amplifier. Now, in case of our musical concert, even though if there is a power amplifier, we do not want distortion there, right? We want the same music output to be coming out of the loudspeaker. Based on the distortion or non-distortion criteria, we will have further classification of amplifiers also. I will tell you that later on. Now, the small signal amplifier will have a high voltage gain, whereas the large signal amplifier will have a high current gain. Let us say in the beginning we will have pre-amplifier and we will have another 2 or 3 or 4 stages of amplifiers, and each one will be having a voltage gain. At the end, we will have a power amplifier or a high current amplifier such as emitter follower. You know that emitter follower gives a large current gain. So, we can have an emitter follower at the end so that it is going to give the high current gain. So, initially we had a voltage gain, later on we have a current gain, together we have a power gain. Now, In the case of a small signal amplifier, only the part of the load line will be utilized. For example, in the load line, when the Q point is at the middle of the load line, when we apply a small signal, let us say microvolt or millivolt or even nanovolt or even picovolt, that signal will be operating only adjacent to the Q point. Whereas the transmitter will not come into complete on or complete off. It will be in the middle of the load line only in the case of a small signal amplifier. But in the case of a large signal amplifier, it is going to use the complete load line where the transistor may go to cutoff region also, or transistor may completely come into saturation region also if it is a BJT. That is where distortion also can occur. To some extent, we can bear the distortion also depending upon the application. Finally, a small signal amplifier has a linearity and gain. Linearity in the sense it is going along the load line only, and we know that only part of the load line is used. So we can say there is no distortion when the waveforms of output and input are compared, and there is a sufficient gain there. But large signal amplifier can be non-linear to some extent, in the sense if it is using the complete load line, if there is a distortion in the output waveform, now linearity may not be there. But the point is linearity can be compromised for the efficiency, which we want, where we want higher power. So where we want higher power, we can use the large signal amplifier for only efficiency, whereas the small signal amplifier is not necessarily very efficient. We had calculated these efficiencies in our earlier exercises. So when we pump a lot of power in watts or in kilowatts into the loudspeaker, we want efficiency also. Almost all electrical systems need more efficiency. Even all engineering systems need more efficiency, in the sense if the electrical systems are not efficient properly, then part of the signals will be lost as heat, and that heat is going to reduce the age of the equipment. More and more heat in the components or in the electronic systems is going to reduce the life of the electronic systems. That way, efficiency is required in case of power amplifiers. And as I have been mentioning about this high current gain, the power amplifiers can also be used for impedance matching. Wherever we have a lower input impedance, higher output impedance, or wherever you have a higher input impedance, lower output impedance, in between them we want to have a impedance matching. Only when impedances are matched, maximum power can be transferred. So the power amplifiers can also be used for impedance matching. Now these are the ways in which we classify our amplifiers. So today's class time is up. In the next class, let me explain more about the other type of classification of these amplifiers. See you in the next class. Until then, take care and goodbye.